Hey guys, this is sample problem 2.6. So for part A, we need to start out by identifying our inventory, and we see that we have 0.042 molar, or if we have a solution, and it's a mixture of 0.042 molar H2PO4 and 0.058 molar HPO4. The first thing to do is recognize that this is a conjugate acid-base pair, so we have a buffer problem. And we have any buffer problem, the first equation you should turn to is the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of the concentration of the base over the concentration of the conjugate acid. Alright, so what this question asks us to do is solve for the pH. We have our acid and our base and the pKa. And what I think a tricky part is about some of these equations when you're using the Henderson-Hasselbalch equation is that sometimes you might not be sure which one's the acid and which one's the base. If you look here, you can tell which one has more protons is going to be the acid. So this one, this H2PO4, has an extra hydrogen, so it can donate a proton, which means it's the acid. This can accept another one, so that would mean that it's the base. So we just plug this all in. We have pH is equal to 6.86 plus log of the concentration of our base, 0.058, over concentration of our acid, 0.042. Alright, and if we plug all this in, we should come out to something around 7. So neutral. For part B, it asks us the same thing, so we have the same setup, only we're going to add 1 milliliter of 10 molar sodium hydroxide. So the first thing we have to do is recognize that 1 milliliter is 0.001 liters, and 10 molar means we have 10 moles per liter. Alright, so let's find how many moles of hydroxide we've added to the solution. Just take 0.001, multiply it by 10, and we have 0.01 moles. Now we need to set up a basic equation. So we have H2PO4, we take the acid on this side, because we're going from acid to base. The acid is being deprotonated, so we're taking away acid and adding base. So H2PO4, big, 2 minus, or just minus, plus OH minus, and that's going to give us, over here, HPO4 2 minus, plus H2O. Alright, so we initially have 0.042 molar, and then we add 0.01 moles, and we have 0.058, and the water doesn't matter, that's a byproduct. These are our species of interest. So 0.01 moles of hydroxide are going to react with this species to completion. So at the end, we'll have 0 here. So subtract 0.032 from this, or 0.01 from this, because all the moles of this will react with this and take away that many moles, right? So if you have 0.01 moles of hydroxide reacting with 0.042 moles of H2PO4, you're going to lose 0.01 moles of H2PO4, and you're going to get HPO4. So this is how much it's going to react. And then so if we lose it here, we're going to gain over here, 0.068 plus, and that's how many moles of water we gain. So now what we do is do the same thing, only we do the same thing as in this problem, only now we have different concentrations. So let's write it all out again. We have our pH, which is what we're trying to find, is equal to our pKa, which is 6.86, plus log of the new concentrations of our species of interest, which are the base, 0.068, base is on top, over 0.032, our acid. And this should come out to something around 7.2. So for part C, we are adding 1 milliliter of 10 molar sodium hydroxide to the solution. Just like last time, only there's no buffer. So we do just same procedure as last time. Begin identifying that 1 milliliter is 0.001 liters, or multiplying that by 10 moles per liter, and that is going to give us 0.01 moles. This is how much we're adding to the solution. And now, as you can see, there's no buffer, so we're not using the Henderson-Hasselbalch equation. Instead, it's a little bit simpler, but first we have to kind of derive some equations we're going to use. First thing you need to realize is that when you have P anything, you have pH. Really what this means is it's negative log of the concentration of H, or H plus, the protons in solution. So what we can calculate right now is we have the concentration of the hydroxide species. So we're going to find the POH. So the POH is going to equal, what, negative log of our concentration of OH minus, which happens to be 0.01. Alright, if you plug this into your calculators, you should come out with 2. So the POH is 2. Now how do you get from POH to pH? What you have to remember is that, maybe you've seen this before, Kw is equal to Ka multiplied by Kb. Alright, and Kw is equal to 10 to the negative 14th. Alright, this is something that you need to memorize. You should know this number here. And so this is the amount of acid you have in the equation, or in the solution. This is the amount of base. You put together, they're stuck in a ratio relative to this constant. So what you want to do is, to be able to find pH from POH, is we're going to take negative log all the way across. Right? So we take negative log of our Kw, which is 10 to the negative 14th, and that's going to be equal to, well, this is our, right? This is the amount of proton, or the acid we have in the equation. So it's going to be negative log of this, which happens to be pH. And when you do, so when you take logs all the way across, this multiplication will become addition. And this is the amount of base we have, so that's going to be our POH. And we'll end up with this equation. And if you plug this in, you'll get 14. Okay? So we have 14 is equal to POH plus pH. And if you just memorize this right here, you can go straight from POH to pH. Alright, so they are in this ratio. So let's solve. Right now it's just some simple algebra. We have 14 minus POH is equal to pH. Our POH is 2, so 14 minus 2 will give us a pH of 12. And that is how you solve an equation given the concentration of hydroxide.